Hi everyone, this is Dr. Geetha, Professor, Department of CSE, Engineering College. In this lecture video, I'm going to speak about the Markov models, the different categories of Markov models, applications of the Markov models, and we'll conclude the lecture with one example of Markov model and hidden Markov model. Categories of Markov models and the definition. What actually is a Markov model? In probability theory, actually it is a stochastic model for randomly changing systems. So actually the states are of different categories. For example, if you take the examples like weather forecasting, speech recognition or stock market prediction. So the next state, in case of weather forecasting, tomorrow's weather is dependent on today's weather. Similarly, in speech recognition, the next phoneme of the audio is dependent on the current phoneme. In market prediction, similarly, future market is dependent on the current market trend. So in all the examples, the states, we call it as the different states, wherein the current state is dependent on the previous state, not the long before states. For such sort of applications, we can utilize the probability theory, which is called as Markov model. So here are the different categories of Markov models. So the basis on which the Markov models are classified are whether the given states are fully observable or is partially observable, and the system we are considering is either having autonomy of its own or it is being controlled by someone. So based on these four parameters, we categorize the Markov models into Markov chain, hidden Markov model, Markov decision process, partially observable, Markov decision process. So in this lecture, we'll focus on Markov chain and hidden Markov model. So Markov chains are nothing but simple Markov models. So the states are all fully observable here, and it is a stochastic model. So it is otherwise called as memorylessness, in the sense that since here the current state is dependent only on the previous state and the before states are not considered here, so it is called as memorylessness. So example we have quoted in the earlier slide, but still another example is how Google predicts the next word when you start typing the search in your Google. So this is an example. So as we stated earlier, the Markov property. The property states that the future states depend only on the current state, not on the previous state. So this is the definition of Markov model. Next, coming to the hidden Markov model. It is actually a category of Markov model where the states are partially observable, not fully observable as like in your Markov model. So in addition to that, here we have certain hidden states and emission probabilities. The application is pattern recognition. The third category is Markov decision process. Here also it applies the Markov property. The only difference is that the current state depends on future directions in multiple ways. So here it deals with the rewards and all. The last category is partially observable state. So here it is, application is controlling the simple agents or robots. So next is Markov random field. So it is nothing but a generalization of the Markov chain, which is in multiple dimensions. Here each state depends on its neighbors in any of the multiple directions, not only in a single direction. So this is a Markov random field. So now the basics of the categories of Markov models are over. Now let us first start with a Markov model, otherwise it is called as Markov chain. So first is, what are all the components of Markov chain? So first component is the set of states. So whatever may be the example we consider like weather prediction or stock market, so you'll have certain set of states. So that's the first component. And second is the initial probability distribution. So initially some state will be there. For example, if you take weather forecasting, initial state might be cloudy or initial state might be sunny. So this is the second component. The third component is the state transition. So initially if the state of a weather is in sunny, might be from sunny it can move to cloudy or some other states. So that you call it as state transition probability. So set of states, initial probability distribution, and then transition probability distribution. So these are the three components of Markov models or Markov chain. Now first, whatever may be the scenario, we have to construct a matrix which is called as the transition probability matrix, and it has got its properties. Three important properties are there. First property is, so it should be a square matrix. So the size of the square matrix depends on the number of states being used there. For example, if you take the weather, you have only two states, so size of the square matrix will be 2 cross 2. And second property is that the entries, when you sum up the row should have 1, which is to be equal to 1. And third property is that the row entry should not have any non-negative values. So these are all the properties of transition matrix, probability matrix. So now let us look into a simple example of Markov model. So first, let us take this where we call it as the state transition diagram. Here we have two states, one is the rainy state, other one is the dryness state. So now with this we'll start with constructing a state transition matrix following the 3 rules. So here the size of the matrix should be 2 cross 2 because here we have only 2 states, rain state and dry state. So this is the state transition matrix, rain state and dry state. So this is the state transition. So for example, from rainy to rainy, the probability of state transition is 0.3. So here rainy to rainy it is 0.3. Similarly, the transition from rainy to dryness is 0.7, rainy to dryness is 0.7. Accordingly, the rest of the entries are entered in the state transition matrix. So if we look into this is a 2 cross 2 matrix, and when you sum up the rows it is equal to 1, and there is no non-negative values in this. So it satisfies the properties of constructing the state transition matrix. Now here we have 2 states, and now the initial probabilities are, so probability of being rainy is 0.4, probability of being dryness is 0.6, just an assumption, we call it as initial probability. Next is the transition probability, as we saw now. So the transition from rainy to rainy is 0.3, from rainy to dryness it is 0.7. So similarly the rest of the transition probabilities are given here. And next comes, we want to identify a sequence. So we have constructed a diagram, we have formulated a matrix. Now an example, let us look into it. So we want to identify the probability of this particular sequence, any sequence we can consider. So in this example, we would like to find the sequence of the probability of initially dryness, and then from transition from dryness to dryness, dryness to rain, and rain to rain. So if we want to find this particular sequence, so first we have to take the different transitions. So initially the state is dryness. So initial probability also we know, the probability of dryness is 0.4. Next is from dryness to dryness. So this is probability of from dryness to dryness, and here probability of dryness to rain. So here dryness to rain. So you call this as probability of rain given dryness. That is the early state was dryness state. From there it is moving to rain state here. Dryness to rain state. So the next sequence is rainy to rainy state. So this is what, now the values are available in the state transition matrix. Initially the probability of dryness is 0.6, and probability of dryness to dryness is, and here it is 0.8, and probability of rainy given dryness is 0.2, and here it is rainy to rainy is 0.3. So when you calculate this is the final probability, which states that the probability of the given sequence dryness to dryness to rain is 0.288. So this is how the Markov models are used to calculate the probability of any given sequence. So the thing is that first a state transition diagram will be there containing the nodes with which we have to construct the state transition matrix, and then if you are given to identify any observed sequence, you can calculate accordingly. Now let us look into another example. So where there are 3 different states, cloudy, rainy and sunny. So here is the diagram. So cloudy, rainy, sunny, and these are all the various probabilities given in percentage. Now to construct the state transition matrix, we require 3 cross 3 matrix because there are 3 nodes here. So here for example, the transition from cloudy to cloudy is 10%, which is 0.1. Cloudy to sunny it is 40%, that is 0.4. Cloudy to rainy it is 50%, which is represented as 0.5. And when you sum up the row, so which is equal to 1 as per the rule of state transition matrix. Similarly, the other entries can be recorded here. Now this is explained like this. If today is a sunny day, then what will be tomorrow? So here tomorrow in the sense we'll start from sunny. Now today it is sunny. Tomorrow there are possibilities like tomorrow maybe sunny is 50%. Tomorrow maybe cloudy is 40%. Tomorrow maybe rainy is 10%. So this is what represented here. Similarly, the other scenario, if today is rainy, then what about tomorrow? The 3 possible transitions from rainy are represented here as percentage of probability. Similarly, if today is cloudy, the various transitions from cloudy, the 3 transitions are represented here. This is another example. Now assume that we want to identify the probability sequence, like if today is Monday, what Wednesday will have the weather. So the weather of Wednesday, we need to identify the probability. So this is the sequence given here. So for which the 3 different possibilities. Initially we know that Monday, that is today, is sunny. So what are the other possibilities? In between the possible changes are sunny, rainy and cloudy. So how we used to identify this is that so let us look into the example, like the probability of the sequence of, for example, if current today is Monday, what is the probability that Wednesday will be a cloudy day if Monday is a sunny day? So how will we identify this? Initial weather condition is for Monday is sunny for all the 3 sequences, because we have 3 different states are there, and the Wednesday we are expecting to be cloudy for all the 3 sequences. In between the possible 3 transitions are sunny to sunny, sunny to rainy and sunny to cloudy. So let us calculate the probability of a cloudy Wednesday as the transition from sunny to sunny, which is 50 percentage, that is 0.5, and sunny to cloudy, the percentage is 40 percentage into 0.4, so which we get 0.2. Similarly, the rest of the possible sequences we are calculating with the formula, so we are getting this value. So finally sum up all the values. So this gives us the probability sequence of, suppose today is a sunny day, what is the probability that Wednesday will be a cloudy day? That is 0.27. So this is another example. I hope that up to this it will be clear regarding the Markov model. So out of the 4 categories, the second category now let us enter, which is called as hidden Markov model. Now what is the difference? Actually hidden Markov model is a category of Markov model. So what makes the difference between these 2 models is that here the environment is partially observable, wherein we have hidden states. Apart from the observable states, we have hidden states. That is one difference. And another difference is with respect to the components. In Markov model we had 3 components, whereas in hidden Markov model we have got 5 important components. So if we take the same weather example, for Markov model, we used to find the possibility of given the current weather, what will be the next day weather. So the immediate transitions we used to see in case of Markov model. And in case of hidden Markov model, if we take the same example, so here hidden variables and observed variables are available. For example, a person wearing a particular cloth can be identified based on the weather of that particular day. So in that case, the person wearing the cloth is considered as the observed variable, and the weather that influences the type of the cloth by the faculty or the person, which is called as the hidden variable. So this is the difference between Markov model and the hidden Markov model. So now coming to the components of hidden Markov model, we told that 5 important components are there. So the first component is the set of states, which is depicted by S. Second component is the state probability transition matrix, like we had in our Markov model. And third one is the initial probability, which is also there in the Markov model. And next is the sequence of observations, followed by the emission probabilities, like what provoked the particular decision of a person wearing the cloth, that is emission probability. So now let us look into an example. So in this example, all the probabilities are given here. This is the initial probability, wherein the initial probability that there will be sunny is 0.6 and cloudy weather is represented as 0.4, that is 40 percentage, which is called as initial probabilities. And next is the transition probabilities of the hidden states. So here we told no hidden states are there. Actually the observables are, for example, this is Lee's hidden Markov model, where we assume that Lee is a friend, imaginary friend, and she used to do for 4 days these activities. She may either paint or clean or shop or cycle. So these are the 4 activities she can perform: painting, cleaning the house, bike, that is cycling, and shopping for groceries. Now let us look into the possibility of, or the probability of, a particular sequence what Leah can do in the next 4 days. So that we will discuss now with respect to this example. So here observables, emission probabilities, transition probabilities and initial probabilities are clearly specified. So as like Markov model, first we need to construct the state transition matrix following the given rules, and we have two hidden variables, sunny and cloudy, for which this is the state transition matrix, and initial probabilities have been given as 60% and 40%. Hidden states are rainy and sunny. Observables are the four activities: painting, cleaning, shopping and biking. Now coming back to the emission probability, so actually it is a matrix that represents the probability of seeing a specific observable given a hidden state. So in this example, the hidden states are sunny and cloudy. The specific observables are painting, cleaning, shopping and cycling. So here it is, and this table is called as the emission matrix table, and this need not satisfy the properties of the transition matrix. Now coming to the three important questions to be asked in hidden Markov model are: what is the probability of an observed sequence? The first question, followed by what is the most likely sequence of states to generate an observed sequence? The third question to be addressed is: how can we learn the values of the hidden Markov model parameters given some data? So now the first question, which is likelihood computation, is addressed by a formula called forward algorithm. The second problem, decoding, which is addressed by the Viterbi algorithm. Third problem, learning the parameters of hidden Markov model, that is addressed by the forward backward algorithm. So I hope that it's clear up to this point. Now coming to the first likelihood. So let us assume that the initial Leah's activity in the 4 days be the observation sequences: painting, cleaning, shopping and bike. Now we want to identify this particular sequence, so for which let us apply the forward algorithm. So as the name suggests, that this algorithm will use the computed probability with the current time step that can be used to derive the probability of the next time step. Since the algorithm moves in the forward direction, it is called as forward algorithm. So now, in this forward algorithm, there are three states: initialization, recursion and termination. So first let us start with the initialization state. So this is the initial probabilities which we saw represented by pi. So 60% chance initially the weather to be sunny, and 40% chances for the weather to be cloudy. So these two are called as the initial probabilities. Now second comes the recursion stage. As many states as we have to start computing the forward variables. And here initially we have completed for painting. Now it is cleaning. So here for cleaning, again the formula is forward variable. If it is the assumption sunny, the forward variable is calculated as the previous forward variable of the state I into the transition probability into the emission probability. So here it is multiplied. So previous forward variable already calculated as 0.24 into multiplied by the transition probability from sunny to sunny, and multiplied by the emission probability. So from sunny to cleaning. So here sunny to cleaning, if you observe, sunny to cleaning, emission probability. So referring that diagram, we are calculating the next forward variable in the recursion first step, and we are calculating for sunny the value as 0.024. Similarly, for the next cloudy, we have to calculate in the similar manner. That is a forward variable for the rainy state. Again, you have to calculate by multiplying the previous forward variable, transition probability and emission probability. This is the previous value, transition probability, and then emission probability. You will get a value. Now you sum up both the values, so you will get the final value as 0.054. So similarly, this already we have calculated during initial probability. It's the first recursion value we have calculated. You follow the same procedure. Start calculating for the second step, again for the cycling step. So this is what the Leah's preference of activities. It is painting, cleaning, shopping, cycling. So we have calculated for all the 4 activities in the given sequence preferred by Leah, and we got the values. Finally, the final value was this one for the sunny state and the cloudy state. So we have to finally terminate this condition. Now how to terminate? You sum up for both cloudy and sunny. This is 0.0028 512 plus 0.0003048. When you sum up, the final probability of Leah's preference in this order for the next 4 days is 0.003156. So this is how the hidden Markov model is applied to solve the problems like this, whether prediction or the sequence of activities a person has the preference to do in the upcoming days. So the only difference between Markov model and hidden Markov models are, in case of hidden Markov model, there are two different states we have. One is observable states, other one is the hidden states, whereas in Markov model, we have only normal states, no hidden states. So I hope that you would have understood to some extent about Markov model and hidden Markov model. So thank you. Now the first form, cloudy.